Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of university salaries. So it's University of Vermont faculty salaries from 2009 to 2021. And we basically have a few features about each employee, their position, their base pay, the department, and the college. And we're going to try to be predicting the base pay based on the other features. So let's hop into the notebook. We're going to use NumPy and Pandas for working with the data, for pre-processing and building our pipeline, as well as evaluating the model. We'll be using the one-hot encoder, standard scalar, column transformer, pipeline, and k-fold objects from sklearn. Our actual models that we'll be using will be a ridge regression model, decision tree, a neural network, and then two ensemble models, so random forest and gradient boosting. Alright, so let's go ahead and import all of that, and we'll load in the data using pandas.readcsv. So we can grab the file path to the CSV file up here. It is in salariesfinal.csv. I'll paste that in, and we can take a look. Alright, so it's a fairly simple data set. We're basically going to predict base pay using the other columns. And there's only one column here that we're not going to use, which is name. The reason is we don't want to try to predict the pay based on the name. We want this to be for any given position in any given department in any of the colleges present, and then also depending on the year. So let's see if we can do that. Data.info will give us if there's any missing values, and it looks like there are no missing values because the number of non-nulls is the maximum number of entries. We also have 4 object columns, which are these categoricals, these two and these two, 3 of which we're going to use, 1 of which we'll drop. Alright, we'll start pre-processing. So it's very simple pre-processing today. Now we're going to be building the models inside pipelines, pre-processing pipelines. So most of the pre-processing, like the encoding, will be done after this phase. So this is more of initial like data cleaning, and there's not much data cleaning to do here. This will just involve dropping the name column. So I'm making a copy so we don't modify the original version by accident. And we're going to drop the name column, so df.drop name from axis 1, and then we'll go and return df. So this we'll call x will be the processed version of data. And you can see we no longer have the name. So this is the data set we're using. And there's only one more thing I want to do here, which is split the data frame into x and y. So we're actually going to do that by setting y to be the base pay column, and x is all the rest of the data. Alright, and we'll return x and y when we're done, and get it back over here. So now x no longer has base pay, that's being stored in y. Now I'm not doing my train test split here. In fact, we're not going to do a standard train test split today, because I'm going to be using k-fold cross-validation to analyze the performance of each model. And k-fold cross-validation is a better way to analyze the model, because the problem with the train test split is that you might end up, just by randomness, by chance, you get a bad test set that is not representative of the train set, or something like that. So k-fold addresses that by using every data point. Basically every training example has the chance of being part of the test set. So let's do this. Before we get into k-fold, I'm going to build the pipeline. So I'm going to create a function called build pipeline. And this is going to take in a regressor. So this is the actual model, the machine learning model that gets passed in. And we're basically going to take that and plug it into a full pre-processing pipeline. So we're going to start by considering what do we need to do to the data. So we have it in this nice form that the user could enter information into. It has 4 fields, or 4 features. Now we want to transform these 3 features into numeric data. So for that we're going to use pandas.getDummies, and take, let's do the college one for example. So x sub college. We get the dummies for this. College is not, oh, it's a capital C. Alright, so these are the college dummies. So here, a 1 represents the original value of a training example. And you can see what the original value is, like so. So this is a one-hot encoding. We're not actually going to use this function. We're going to use a one-hot encoder object from sklearn, which will just do this for us. It allows us to pass in a data frame that has all the columns we want to encode, and it will automatically create the dummies for us. So we want to actually embed this in its own pipeline. So what I'm going to do is call this nominal transformer, because these are called nominal features, these categorical features with no ordering between their values. And we're going to create a pipeline whose only step is a one-hot encoder. So like that. Here's our nominal transformer, and this is what we're going to use to one-hot encode the data. Next, we need a way to tell the model which columns to use this nominal transformer on. So now we're going to create our preprocessor, which will do this for us. That will be a column transformer object from sklearn, which takes in a set of transformers. In this case, there's only one, which is the nominal transformer we just created. So we'll pass it in. And we also pass in the columns we'd like to encode. So in this case, there's only 3, which is primary job title, department, and college. So I'll just copy those in here. And now we're almost done. We're now going to use this preprocessor in the actual model building. So now we create the model, and this will be a pipeline itself, whose steps go as follows. First, we have the preprocessor, and that's just going to be the preprocessor we created, which will one-hot encode the proper columns. Then we will have our scaler, which will scale the data so that each column has the same range of values, which will improve the performance of a few models. So standard scaler. The standard scaler actually just gives each column a mean of 0 and a variance of 1 by doing a shift and scale on each column. And then finally we'll have our regressor. And the regressor is coming through as the argument here, or parameter. So we just pass that in. And this will be the full model. This model will allow us to take in some data that looks like this and output a prediction for the base pay. Alright, we're just going to return model down there. Now before we continue, there's a few things I have to address. The first, the one-hot encoder. I'm actually going to include sparse equals false here, so that we don't get a sparse output. And handle unknown equals ignore. And what that means is, let's say when we do the train test split, or the k-fold, we have our train and test set. Let's say there's one training example. Let's say there's only one occurrence of this training example. And what I mean is one occurrence of a value in here. So let's say, I know that's not true, but let's imagine there's only one professor example. If that professor example ends up in the test set, then when we fit this model, the one-hot encoder is not going to see that professor example, and is not going to create its own separate column for it. Then when we try to evaluate the model on some new data that has professor, it'll throw an error. So what handle unknown does is, instead of throwing an error, it just ignores that if that case arises. The last thing I want to do is in here specify remainder equals pass through. And this is very important because if you don't have this, then any columns that are not affected by the transformers listed in here will be dropped from the data. So by including this, now the column transformer will apply the one-hot encoding to these 3 columns, but it will still leave on the year column, which is not touched by the transformers. Alright, and there we go. So this is our pipeline function. And now I would like to test it out. We can try it with 1. So let's build a pipeline for a ridge regression model. So this is what I imported at the top. This is just L2 regularized linear regression. And we can specify an alpha value in here, which is the strength of the regularization. Maybe we'll give it 10. And so this should generate a full model using a ridge regressor that will take in the data. It will pre-process it accordingly by one-hot encoding these 3 columns. Then it will scale the data, and then it will pass it into the ridge model. So if we let's call this model, and then we try model.fit on, okay, well, we can't quite do this yet, so I'm not going to, because I don't want to fit it on, I mean, technically we could fit it on the whole data set, fit it on all of XY, just to show you that it works, but I would never recommend doing this, because we don't have anything to score it on now. I could score it on itself. We're going to get artificially high results. This is the R-squared score, because it can overfit doing this. You never want to use the same set that you trained on for scoring purposes. Always want to keep your separate set of test data. Okay, so I'm not going to create a model like this. I'm going to create a bunch of models. I'm not going to fit them yet. So let's make a dictionary called models. And this is going to map the name of the model. Sorry, it's a linear regression, which is a ridge model, so I'll say ridge. And I'll map that to the actual instance of the model, right? So we're going to do that for decision tree as well. I think we have 5 models. This is a decision tree regressor. Then we have our neural network, and this is our MLP regressor for multi-layer perceptron. And we'll have a random forest model. This is a random forest regressor. And finally, gradient boosting. So this is a gradient boosting regressor. And if you're not sure about what these are, essentially random forest and gradient boosting both use decision trees. But this one, they're ensemble methods, so they use a bunch of different little models. This one builds decision trees in parallel, and this one builds decision trees in series, one after another. Alright, so we have our models. Let me just indent these so it's a little nicer to look at when we evaluate them later. And then what I want to do next is actually start with a k-fold. So there's our models, and now we're going to do our model selection with k-fold cross-validation. Alright, so what I want to do, so essentially the way k-fold works is it divides the data set up into k different sections. And we decide k. The standard values for k are 5 or 10, but it doesn't really matter. Just know that the larger k you have, the more data that the model will have to train on in a given iteration, and the less data the model will have to test on. So you want to find some balance, but it's really up to you. So we'll use k equals 5 in this case. So we'll evaluate the model. I should also point out that with a high k, it actually is more computationally expensive as well. So the evaluate model function will take in a model, an x, and a y. And what this will do is essentially it'll split the x and y into 5 different sections, and it'll iterate through each section, and each time it uses that section as the test data. So for the first iteration, it uses that for test and uses the other 4 sections for training. After that, it moves on to the next one, uses that for test, and uses the other 4 for training. And the reason we do this is a good thing to do is because you get a variety of test sets. You get to see how the model is doing on all different sections of the data, as opposed to just doing one train test split and hoping it's a good model. So before we do this, I actually forgot one step in our pre-processing. Before we split it, I need to shuffle the data, because normally shuffling the data is handled by the train test split function, but we're not using that today. So let's shuffle the data. So to do this, we just type df.sample, and we're going to sample 100% of the data without replacement. So fraction equals 1.0, that means sample all of it, which is just the same as shuffling it. And then we'll reset the index afterwards, and include drop equals true so the old indices don't become a new column. Alright, so now the data has been shuffled. I think we're good to go now. So inside here, what we want to do is create our k-fold object. So I'll call it kf, and that's just going to be a k-fold object from sklearn, which basically just does all the work for us. We pass in a number of splits, that's our k. Let's make that 5. And then we can iterate through for train index test index in kf.split x. What this is doing is essentially the split function actually splits x into 5 different sections, and then provides indices for the train and test sets for each section. So for each split. So for iteration 1, the test index would be the first bunch of examples, or the first fifth of the data, and the trained index would be the last 4/5 of the data. For iteration 2, the second fifth would be the test set, and the first fifth and the third through fifth fifths of the data would be for training, and so on until we get to the end. So this will go 5 times, each time using a different set of data as the test index. So each time as we're going through, we're going to fit the model. So we'll call model.fit on just the train set. So here the train set is given by x indexed with iloc, which is index location. And we're going to pass in the train index here for the rows and all columns for the columns. And so what this is saying is use only the parts of x that have indices given by train index. So this is essentially the train set for x. Now we also need to fit it on the train set for y, so that's just y.iloc train index. And we don't need to include this number of columns because this is a single one-dimensional series. Alright, once we fit the model, we're going to make predictions. So here, let's create the predictions, call them pred, and we'll call model.predict on the test set. So test set here is given by the same thing, but using the test index. Alright, so these are our predictions. And now what I want to do is calculate 2 metrics. So that's going to be the Rmse and R² scores. Well, first we'll do Rmse. So the Rmse is just the root mean squared error, and it's calculated by taking the true values minus the predictions. So we'll get the true values by y.iloc test index. That's the test value, the true target values for the test examples. We subtract the predicted values. So this will be the error. What we do after that is square it. So we get the squared error, squared errors for each one. Then we take the mean, which will be the mean squared error across all examples, the average squared error. And then we'll do a square root to return the unit back into the original target variable's unit. And so this is a way of understanding the average error across all examples in the same unit as the original target variable, which in this case it may be dollars, I'm not sure exactly, whatever the base pay currency is. Okay. And then we're going to, okay, so what I want to do, because I want to take, so the way we want to evaluate the model is by finding the average Rmse across all iterations of the k-fold. So what I want to do is actually store this value up in some list up here. I'll call it Rmses, and that'll be that empty list. And we'll just append this to it, rmses.append Rmse. So that'll throw this value up into this list. And we'll do the same thing for the R² score. So R² score is calculated by taking the sum of squared errors for your model, which should be numpy.sum of y.iloc test index minus predictions, and then the square. So that's similar to what we did up here, but this is the sum instead of the square root of the mean. This is the sum of our squared errors, and R² score is is like a relation between this value and the same sum of squared errors, but for the baseline model. So the baseline model means what model would you use if you had no inputs available to you. So if we replace predictions with that model's predictions, we'll get the baseline errors. So the baseline errors would basically just be the mean of whatever y we're using. So the mean of the test set. So if we do y.iloc test index dot mean, that would be our prediction every time for the baseline. And so we get the errors of the baseline model. This is the sum of squared errors. In that case, then the R squared score is our errors divided by the baseline errors, and 1 minus that whole quantity. So that's R2. And what we'll do after that is make another list up here called R2s, and we'll append this value to that list. Alright, so the reason I threw them up into these lists is because I want to return now, say return the average Rmse and R squared. So we're going to return numpy.mean of Rmses, and I'm also going to return numpy.mean of R2s. So we'll get the average Rmses across all k-fold iterations, and the average R squared score across all k-fold iterations. Alright, so that is the function we're going to use to evaluate the model. So now all we have to do is basically iterate through our dictionary for name and model. Let me actually note, we can do this a little better. What we could do is iterate through this dictionary, taking each name and model, passing that model into a build pipeline function, and then running the predictions. But we can actually just do this beforehand and use build pipeline over here, like that. So we'll build the pipelines first, like so. So now we have the pipelines already built in, and we are ready to just evaluate those models. So now a given model is actually a pipeline with a given regressor. So for each name and model in models.items, and .items will return these key value pairs as tuples so that we can iterate through 2 at a time. We're just going to fit the model, model.fit. Sorry, we're not going to do that. We actually just have to call this function. This will do all the fitting for us, right? So we're going to print out the name of the model, followed by the Rmse. We'll display it to 2 decimal places, and format this using evaluate model on model, x, and y. And this will give us the Rmses for each model. And we have a problem. Oh, right. Okay, so this actually returns 2 values, the mean Rmse and the mean R squared. So I only want the Rmse in this case. So we're just going to do sub 0 to get back the first value it returns. And then once that finishes, we'll go down here and do the same thing for R squared. And we'll display the R squared to 5 decimal places. It's going to be a value between between negative infinity and 1. So after that, we just change this to 1 so that we get back the second value it returns, which is the average R squared score. Alright, I'll run this, and when this finishes, I will resume the video. Alright, so the model's finished training. And I would like just to point out that this did take quite a bit longer than your traditional train test split approach, because it had to build 5 models for each of these. So this whole thing, I had to run it twice. It end up taking about 10 minutes or so to complete. But we can now have analyzed the performance of the models, and we can almost be sure that these scores that we're getting are much more reliable than if we were just to use a single train test split to analyze. So we want the lowest Rmse possible, and that looks like actually the linear regression model beat all the others. So it looks like maybe here a simpler model is better than a more complex one. Although I would like to also point out we did not really do any hyperparameter optimization. If we were to, it would take even longer because we'd have to optimize across different parameter settings within each iteration. But yeah, in general, it looks like the linear regression is performing the best. And the R squared scores, we can also see that as the highest R squared score. And the worst model here seems to have been the gradient boosting model, which has the lowest R squared score as well. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.